Hi everyone, in this video I'm continuing to work through question 15 part C of the 2020 Extension 2 trial exam from North Sydney Girls. So I've just worked through part 1 in a prior video, so take a look at that if you haven't already. And in this video I'm going to focus on part 2, which tells us to let AX vector be equal to mu AB vector, where mu is a scalar between 0 and 1, so essentially a fraction. And you can kind of see that from the diagram in the question. The vector AX is clearly some fraction of the vector AB because X lies between A and B. We're then told to use vector methods to show that the line OX divides the line AB in the ratio of the lengths of the adjacent sides. Or in other words, AX to AB, that ratio, will be equal to OA to OB. So yeah, let's take a look. So I've written out what we're being asked to show along with this hint. And I think the first thing worth noting is that what we're being asked to show in terms of ratios, you could restate that as essentially being AX, that line, and XB, that line. They're the magnitudes of the associated vectors. So it's the magnitude of AX vector divided by the magnitude of XB vector, that ratio, or that one number divided by another, that fraction, we're being asked to show that's going to be equal to the magnitude of OA vector, which, remembering in the context of this question, is A vector, that was A vector is the vector OA, divided by the magnitude of B vector. That's essentially what we're being asked to show. If we can show this, then we've shown that these ratios are equal. So noting that, we've already got a statement about, or a hint about what we should do with AX vector, this first vector up here. So I think a natural next step is to think about what is XB vector, how can we state that, and preferably we can state it in some format involving mu, I think, so that we can then simplify this left-hand side and then see if we can show that the right-hand side can be simplified to the same thing. That's the basic strategy of this question. So let's start by thinking about XB vector, which if we go and take a look at our diagram, if I want to get from X to B, that vector, I could really just state that as going from A to B and subtracting from that A to X. That's kind of because they're lying on the same line. That's just an alternative way to think about the XB vector. XB is the whole vector just minus this AX component, and I think that's a helpful way to think about it. So let's write that out. So XB vector is the whole line AB vector minus AX vector. And because we've already got AX, we've been given this hint as to how to think about AX, we can write that as AB vector minus mu AB vector. And now we can see why it's helpful to think about XB in terms of the whole vector AB minus AX, because now we've got two ABs. So we can write that as 1 minus mu times AB vector. So now what we could do is we could write this fraction. We could say therefore the magnitude of AX vector divided by the magnitude of XB vector, we can write that as the magnitude of AX vector, which is just mu AB vector, divided by the magnitude of XB vector, which is 1 minus mu AB vector. And because mu is a scalar, we can really just bring that out of the magnitude. So we can say that's mu times the magnitude of AB vector on 1 minus mu times the magnitude of AB vector And now those two AB vectors cancel, so that we've got mu on 1 minus mu is the ratio. So the left-hand side fraction, we've been able to restate as mu on 1 minus mu. So now our task is to show that the magnitude of A vector on the magnitude of B vector can also be shown to be equal to mu on 1 minus mu. And if we can do that, then we've solved this question. Now, at this point, whilst this part 2 didn't use the word hence, actually we are going to, I think, benefit from relying on what we worked out in part 1, because in part 1 we've shown that OX vector is equal to lambda A hat vector plus B hat vector. I think it kind of makes sense to consider how working from that result might help us over here with this right hand side. So let's say from part 1 we can say that OX vector is equal to lambda times the sum of the unit vectors, A hat vector plus B hat vector. And so it makes sense to see if we can come up with some other way to write OX vector that then allows us to somehow get mu involved. So we can also state that OX vector, if we come back to our diagram, to go from O to X, one way we could do that is we could go from O to A and then A to X. So let's go with that. So we could go from O to A, and then we could go from A to X. And the reason that's a good idea, going from O to A and then A to X, is because we know A to X has mu in it, or we can write that with a mu in there because that's the hint we've been given in the question. So we can say OX is also OA, which we know is a vector. That's how it was defined in the question. And then we can just say plus mu times AB vector using this hint here. And so now let's think about AB vector. So AB vector, we could, if we want to think about how we can get from A to B, we could go from A to O and then O to B. So let's see where we get to there. So we could go from A to O plus O to B. And A to O is just the same magnitude of O to A, just the opposite direction. So we could write that as negative A vector. And then OB is just B vector as it was defined in the question. So we can just write that as B vector. And from there, we can put that back into our OX. So we can say, therefore, OX vector is equal to A vector plus mu times negative A vector plus B vector. And then it probably makes sense to expand the mu. So we get A vector minus mu A vector plus mu B vector. And from there we can just factorize. So we'll get a 1 minus mu times A vector plus a mu times B vector. And that's looking positive because we've got a mu and a 1 minus mu flying around, and we know we want to work out something with mu on 1 minus mu. So hopefully we can get there somehow. Now the key to it will be the fact that we've got two different versions of OX vector. So the next natural step is to set them equal and see where we get to. So I might have to turn over at this point, but we can conclude that lambda A hat vector plus B hat vector. So therefore lambda A hat vector plus B hat vector is equal to 1 minus mu A vector, 1 minus mu A vector plus mu, which is plus mu B vector. And this is looking pretty good, but the issue we need to deal with now is that on the left-hand side we've got the unit vectors, A hat and B hat vector, but on the right-hand side we've just got the the original vectors. So ideally we'd want the same thing on both sides, and the way we can create that link is we can use the kind of foundational definition of a unit vector. So if I start with a hat vector, going back to the definition of a hat vector is it's the original vector divided by the magnitude of that vector. And same deal with b hat vector. B hat vector would be equal to b vector on the magnitude of b vector. So therefore what we can say is if I isolate a vector and b vector and then have something to put in over here on this right hand side, we can say a vector is equal to the magnitude of a vector times a hat vector, and b vector is equal to the magnitude of b vector times b hat vector. So therefore, throwing those two into the right hand side, we get lambda, and I'll expand this at the same time, so lambda a hat vector plus lambda b hat vector is equal to 1 minus mu times a vector, which we can write as the magnitude of a vector times a hat vector, plus mu times the magnitude of b vector times b hat vector. So now we can equate coefficients, because on the left hand side we've got something times a hat vector plus something times b hat vector. On the right hand side we've got something times a hat vector plus something times b hat vector. So therefore, by equating coefficients, it might not be the perfect way to say it, but hopefully you get the idea. We can say that lambda is equal to 1 minus mu magnitude of a vector, since lambda is what is in front of a hat on the left hand side, and 1 minus mu magnitude of a vector is what's in front of a hat vector on the right. And then same deal, we can also say that lambda, which is what is in front of b hat vector, is equal to mu times the magnitude of b vector. And therefore, if both of these are equal to lambda, we can conclude that 1 minus mu times the magnitude of a vector is equal to mu times the magnitude of b vector. And noting that we're trying to find something in terms of mu on 1 minus mu, it makes sense to bring the 1 minus mu over here and bring the magnitude of b vector over here. So therefore we can say the magnitude of a vector on the magnitude of b vector, so bringing that down, will be equal to mu, and then bring the 1 minus mu over. And that's what we wanted to show. We wanted to show that the magnitude of a vector on magnitude of b vector is also equal to mu on 1 minus mu. So therefore, to bring it all together, we can say that the magnitude of ax vector on the magnitude of xb vector, ax vector on the magnitude of xb vector is equal to the magnitude of a vector on the magnitude of b vector, which is equal to mu on 1 minus mu. We showed both of them were equal to that. And therefore, because that is the equivalent of our original question, we can conclude that ax to xb, that ratio, ax to xb, is equal to OA to OB. OA to OB, and that's as required. That's what we were being asked to show. So yeah, actually quite a bit to that when you kind of reflect on it. And quite a tricky one, I guess, because the hint is not, I mean, it's required. It gives us a good steer, but it doesn't really give you too much to go on. I guess for me, I found it quite helpful to kind of adjust this ratio format that the question was written in to more of a fraction format, because I think it's just a bit easier to deal with. And I think a lot of the effort with this question is I guess appreciating that these are the length of lines, but the question ultimately is about vectors. So we're focused on not the vector, but the magnitude of the vector. And then once we get these magnitudes of vectors, we can we can start to make use of all the vector techniques. And I think once I saw this AX on XB, well, given we already were given the hint about AX, it just made sense to think about XB. And then working out that ratio kind of then led to the next natural step, which is prove that the right-hand side can be shown to be the same thing. And then, whilst the question writer didn't give us a direct link between part 1 and part 2, I think it's always worth considering how do subparts of a question link, because often the reason a question is broken up is it's the question writer trying to scaffold it, which basically means break it up into little chunks. So really, you can think about question 15C as being one question, and you know, it's possible that on a harder exam, the question writer could just give this and not give part 1 as a hint and just go straight to part 2, and you have to work out that doing this step is useful. But you know, that might be a bit too hard in the context of high school and the HSC. Maybe that's fair enough at university, but in high school you'll often see that they break it up into chunks to give you the guidance. So you're always looking for those links. Often question writers will use the word hence to kind of be very clear about the link. Here they haven't, but that doesn't mean you shouldn't look for the links. Still look for the links. And here we made use of what we showed in part 1, which kind of gave us the hint, well, we've got one version of vector OX, find another one, and then effectively through simultaneous equations we were able to show that the right-hand side was equal to the same thing. So there you have it for that question. Hopefully it's all made sense and you followed along, and tick boom.